Hi friends, today we are going to discuss about ferromagnetism. If you consider any magnetic specimen, there not only the magnetic treatment, any type of material, it contains some millions and trillions and hexillions of atoms. That is, if you just take one molar volume of a material into your hand, there will be Avogadro number of atoms present in it. That is, if I take one molar volume of a material, it will contain 6.023 into 10 to the power of 23 atoms. And if I come to the magnetic materials, the total magnetic moment of a specimen is the result of the magnetic moment of the individual, that is this many number of atoms present in it. And in our last videos, we have discussed about diamagnetism and paramagnetism. In diamagnetism, the magnetic moment of the individual atoms will not be there. That is, for every individual atom, the magnetic moment is zero. And in paramagnetism, for individual atoms, there will be a little bit of magnetic moment, but the magnetic moment of different atoms are not organized in a single direction. Now, if we come to the ferromagnetic materials, the property of the ferromagnetic materials is that some group of atoms will have their magnetic moment oriented in same direction. That is, if there will have many atoms in a material and some particular group of atoms will have the magnetic moment oriented in the same direction. That particular group of atoms are called domains. Let's see those domains more clearly. Suppose this is the ferromagnetic specimen, and I have taken the domains in different colors just for the visualization, and these are the different domains. The domains doesn't have any different meaning. Domains are nothing but group of atoms whose magnetic moment is oriented in the same direction. That is, if you take this particular domain, suppose if this domain has some only two atoms, then the magnetic moment of those two atoms will be in the same direction, right, as we see from the figure. Then different domain had, but not all the domains that are present in the material are oriented in the same direction. That is, this domain has some different direction. That is, magnetic moment of this domain is in another direction, and magnetic moment of this domain is oriented in different direction. Not only on the surface, but if you go deep into the material, then also we will see the same. See, if I if I remove the top and sides of the material, and I am able to see the inside view of the specimen, and there will be many group of atoms that are present inside the material. Suppose consider this domain. This is one domain, and it will have the dipole moments oriented in this direction, and this is another domain. Okay, and this is another domain whose magnetic moments are oriented in this direction. That is, magnetic moments of domain are oriented in the same direction, but not all the domains have the magnetic moment oriented in the same direction. That is, different domains will have the magnetic moment in different direction. Now we will see what happens when you apply the magnetic field. Suppose if I apply a magnetic field in this direction, now see, the domains are oriented, all the domains are oriented in the same direction. See, this domain, every domain will have the same dipole moment in the same direction. Not same dipole moment in this similar direction. That is, ferromagnetic material has huge magnetism, very huge magnetism. See this, every domain has the magnetic moment along oriented along the direction of the magnetic field. So this gives us the susceptibility of the ferromagnetic material size far more. That is positive value, and it will have some huge value. And relative permeability of the ferromagnetic materials are also far greater than 1. Now we have seen diamagnetic, paramagnetic and ferromagnetic materials, and we will see two laws called Curie law and Curie stress law, which defines about the magnetic susceptibility. Just now we have discussed that the magnetic susceptibility of ferromagnetic materials is positive and very huge value, right? And the Curie's law, if you see the Curie's law, what it says, susceptibility is equal to C by temperature. C is the material specific, that is, the susceptibility of a material is inversely proportional to the temperature. That is the main concept that is involved in the Curie's law. If you, now we will see it symbolically. Okay, see, many dipoles are oriented in the same direction. What happens when I increase more temperature? When I increase the temperature, due to the thermal agitations, these dipoles will go back to their original positions, that is earlier positions, that is they won't be oriented in the same direction. That is magnetic susceptibility will decrease as we increase the temperature. Okay, that means susceptibility is equal to C by T. And not all paramagnetic materials will obey this Curie's law. Some will deviate and they follow another law called Curie's Weiss law. The relation is same, but it is not inversely proportional to the temperature, but is inversely proportional to the T minus theta. Theta is the Curie temperature. Many ferromagnetic materials, not many, every ferromagnetic material will follow the Curie-Weiss law. What is theta? Is a Curie temperature. What is Curie temperature? Is the temperature at which a ferromagnetic material will convert into the paramagnetic material. That is, their magnetization will break and the orientation of the magnetic moments will break and they orient in random directions. That is, they won't have the magnetic moment. The temperature at which the ferromagnetic material will get converted into the paramagnetic material, that temperature is called the Curie temperature. Thank you. If you like the video, please subscribe.